Greetings, space enthusiast. You're now tuned into Space Forward.
I know a lot of people in the field of SETI are in it because they expect there's something to find in their lifetimes. And I know that Frank Drake and others expressed that optimism that a detection would be made. And I don't know. But I do know what Cocconi and Morrison said in their original paper that got this all started, which is that if we don't look, we definitely won't find anything. And so I'm excited to be in the field when it's so young. And there's still so much looking to do that no one's done before. And so I don't know the odds, but they're much better today than they were even 5 years ago.
We're your host, Hussein Bukhari
and Kelly Kowalski. Get ready to embark on an interstellar expedition
with forward-thinking space visionaries to explore the latest intriguing ideas
that are making our space future a reality.
If we were to keep doubling our computing power too many more times, that would be a huge problem. Ultimately, the solution is that you've got to use that energy somewhere else, not on your biosphere. So yeah, if we're looking at Earth's technosignatures, my hope and expectation is that the long-run future of humanity with a sustainable biosphere involves pushing a lot of that stuff off planet.
Tune in now to blast off with Professor Jason Wright of Penn State's Extraterrestrial Intelligence Center. We discuss the search for alien technologies and where we could house our future computer power to preserve our own planet.
Let's do it.
Okay, so in our last episode with Professor Alex Ellery, we found out why Ellery decided to move away from pursuing astrophysics, and instead he decided to pursue robotics.
You're right. Ellery became a skeptic about intelligent life elsewhere in the galaxy. So definitely check out our previous episode about Ellery's reasoning there.
Right. So now in this episode, we're talking to a proponent of extraterrestrial intelligence, or at least the search for ETIs, aka SETI, and specifically searching for alien technologies or technosignatures. And this is the real science that is taught at Penn State under the tutelage of Professor Wright. And for the record, I am not talking about UFOs or UAPs. Did I tell you I got the most traction ever on social media because I called all the UAP news stories clickbait journalism?
What?
Yeah, so thanks to all the UFO fanatics out there who took my comments and ran with it. But seriously, it's very ironic to me that these same folks aren't more obsessed with the actual, real, mind-blowing science that is behind SETI, like the search for technosignatures on, say, other planets or other solar systems.
Like detecting the energy output from a Dyson sphere?
And a Dyson sphere is?
It is a swarm of artificial satellites that could theoretically surround a star and capture its thermodynamic potential.
Yeah, and searching for more down-to-earth technologies like light pollution that you would see around our own planet, or gas signatures that might indicate artificially induced climate change.
Yeah, and what's interesting about this episode and our previous episode, both Ellery and Wright argue for the utilization of space, because even now, and more so in the future, we're going to have to think about long-term preservation of our biosphere.
I know, right? That we're going to have to push a lot of industry off Earth if we want to balance our insatiable desire for resources and more computing power, and do that while maintaining our planet's ecological integrity.
Yeah, I mean, there's no place like home, right? So, on that note, let's dig in with Jason Wright and find out why he thinks that the search for technosignatures are equally important as the search for biosignatures.
Well, welcome, Jason, to Space Forward. One of the things I super appreciate about you is your ability to clearly explain complex topics like what we're going to talk about today, technosignatures. And I heard you give a talk at Breakthrough Discuss, and in a fun way, you gave a talk that pitted biosignatures against technosignatures. Can you walk us through your proposed smackdown to these two fields and tell us who wins in the end?
Yeah, so I want to start by saying that this shouldn't be a fight. That we want to know if there's life elsewhere in the universe, and there really are two obvious ways we can go about looking for it. We could look for some sort of sign of metabolism, some kind of biosignature that might be gases in the atmosphere of a distant exoplanet, or it might be fossils on Mars, or even like fish swimming around in the ocean under the ice of Enceladus or something. But we could also look for signs of technology, and a classic one might be radio waves. Because after all, we give off a lot of radio waves. And if you were an alien around a nearby star and you were looking back at the sun to try and see if the solar system had life, the most obvious sign of life in the solar system is probably our radio waves. And so whether we should be looking for biosignatures or technosignatures, both should be avenues that we explore kind of all under this umbrella of trying to figure out if we're alone in the universe. And so in terms of pitting them against each other, I would hate to say we should do one and not the other. I really do think that we should pursue both. And the reason that I framed it the way I did at Breakthrough Discuss is that despite a lot of popular perception to the contrary, NASA, for all of its talk about trying to find out if we're alone and exploring alien life in the universe, it spends virtually none of its resources looking for technological life. And that goes back to the 80s, actually, when Congress cut out of NASA's budget any references to looking for technological life with radio waves. And that happened, twice that they completely canceled out a program. And finally, NASA just sort of learned its lesson institutionally that it would not have anything to do with the subject at all, lest it attract unwanted attention from Congress. And so until recently, NASA has done virtually nothing in that regard. So, a lot of the public thinks that NASA has all these radio telescopes looking for radio signals from aliens, and it does not. And so that's the context in which we look at all of the ways NASA is looking for life. We're exploring Mars. We're going to go explore Europa. Hopefully we'll explore Enceladus. And we're using these great observatories to look at exoplanets that might be like the Earth with the long-term goal of seeing if they have life. So NASA's spending literally billions of dollars on this question, but only looking for biosignatures and virtually nothing on technosignatures. And so that was the context where I wanted to point out that that balance of funding that NASA currently has doesn't make any sense. So it might make sense if we thought biosignatures were much easier to detect and much more common. That would kind of make sense. If we thought biosignatures are more likely, then you want to match your resources to your expectation of what it is you might find. So in that sense, looking for technosignatures might be worth a little money, but if it seemed like a long shot, like a lottery ticket, you don't want to spend too much on it. So what I wanted to walk through is where this perception comes from, that biosignatures are a much better bet, at least when we're talking about outside the solar system. And I think it actually comes from the Drake equation. The Drake equation is foundational to the field of SETI, the search for technosignatures. It was written down by Frank Drake right at the dawn of modern SETI in 1961. And he just wanted to get his hands around the problem of whether it was worthwhile to point radio telescopes at space and look for alien signals. And so he wrote down, it's an impossible question, right? Are they out there? We don't know. We just don't know if they're out there until we look. But he wanted to know if it was plausible or not. Like, what would we have to assume in order for SETI to succeed? And so he wrote down his equation. The number of signals that there are to find is equal to a whole bunch of parameters. And it starts with the birth rate of stars in the galaxy, how many stars form every year. And then each term shrinks that number down. How many of those stars have planets? How many planets per star? How many of those planets are like Earth? How many of those planets actually give rise to life? How many of those planets give rise to complex or intelligent life? How many of those planets have life that communicates and sends out the signals we're looking for? And then finally, how long do they do it? Because if they only do it for 5 minutes, the chances we'll find them are very small. And so you put all those together. And the intuition there is that there are way more planets with life than there are planets sending radio signals. And so unless you think radio signals are an inevitable consequence of any life at all on a planet, you seem much better off going for biosignatures than technosignatures. And that is what the equation implies, but that's not actually a good assumption. And so this was the point of my talk one of the points of my talk that you were referring to, is that it doesn't even work for the solar system. Like, you're back on Alpha Centauri, you're looking back at the solar system, you want to find signs of life. You could try to detect the Earth, try to detect its biosignatures. But, if you accidentally look at Venus instead or Europa from Alpha Centauri, there's nothing. You're not going to find any signs. And then even looking at the Earth, what exactly do you need to pick out? It's a very challenging problem. There are biosignatures, but it'd be hard. But if you pointed a sufficiently strong radio telescope at the Earth, you'd see our signals. But also, if you pointed that telescope at Mars, if it was sensitive enough, you would also detect our technosignatures, and also Venus, and also the outer planets and interstellar probes. We're spreading our technosignatures. So, and that number of signals there are to find for the solar system is actually more like 4. But for biosignatures, it's only 1. There's only 1 planet that has biosignatures. And so this is the point that is behind the so-called Fermi paradox, that wonders, if they exist out there, why aren't they here right now? Why haven't they traveled here? And, there are a lot of answers to that, but the logic behind it is, if they exist and they can do something we can detect, they can almost certainly travel among the stars and among the planets in their system. And that can greatly increase the number of places where there are technosignatures. And like Mars, you can have planets or even star systems that have technosignatures, but not necessarily a planet with a biosphere. And so you can have technosignatures without biosignatures. The other comes from the L in the Drake equation. We imagine that because Earth has had 4.5 billion years, 3.5 billion years, something, of lots of life on the surface. But we've only been giving off radio waves for decades, that technosignatures are brief, that they are a small, insignificant fraction of a biosphere's life. And so just from the numbers there, you expect them to not be very abundant in the galaxy. But again, that's only looking backwards. So we've only been producing them for decades, but there's no reason we'll stop producing any kind of radio waves. Even as we go to fiber optic transmission and things like that, radio waves will always have their use. If for radar, then nothing else. And we give those out all the time. Radio waves from radar escape and are detectable. So looking to the future, we expect we'll be using them for much more than many decades. And maybe you're pessimistic about humanity's future on Earth. That's fine. First of all, you shouldn't project that onto aliens. But also, secondly, unless we somehow go extinct, completely extinct, we'll keep doing it. Like, we could have some sort of global climate catastrophe that reduces human population to, 100,000 people. But that's still 100,000 modern humans that have, the records of Wikipedia and stuff. I mean, we'll figure it out again. We'll come back on a cosmic timescale. Unless we go extinct, we're going to be using technology. So the future of our technology, who knows? I mean, it's basically unlimited. The biosphere will go away. Eventually, give us 500 million years, the sun will get so bright, just in the normal course of stellar evolution, that it'll boil the oceans off and Earth will lose its biosphere. But there's no reason our technosignatures have to stop. We're already on Mars, right? And who knows how far out we could go. So the point is that the technosignatures are already, our technosignatures are already just as detectable as our biosignatures, if not more so. They're potentially much longer lived, and they're potentially much more ubiquitous. And so when you do all of that reasoning, there's this long tail. It's very possible that technosignatures are by far the better bet if you want to find life in the universe. And so my punchline was not that they win. It's that there's a strong enough case, a maximal case that can be made that justifies better balance of funding between the two approaches.
Okay, so you brought up Frank Drake, and the first time I think I heard about you was through the SETI Institute because you won the 2019 Drake Award. So congrats on that.
Thank you.
But tell us perhaps why you won the award, and now why are you going after Drake or the Drake equation?
Go after Drake. So let me clarify. The reasoning of the Drake equation is really profound, and it has, its purpose is to justify SETI and show that it's a worthwhile endeavor. And so it doesn't really try to be precise. It's not like there are this many in the galaxy. We don't know what the terms in the Drake equation are. It was not supposed to be it was supposed to be a sufficient argument. Like, even if you don't consider travel, and even if you think technosignatures don't last very long, you still end up with a number that's worth looking for. And so the fact that the true number could be much, much higher is just even stronger evidence for what he had already concluded from it. So the equation has really served its purpose very well, and has served as a roadmap for astrobiology. I mean, even people not looking for technosignatures, they think about the problem of biosignatures in terms of the Drake equation. And if you take a course in life in the universe, the units in that course all semester long basically track the Drake equation. It's been a wonderful way for the whole field to organize its thoughts. And so I didn't mean to dismiss or minimize Frank's work with that. Frank's a hero of mine for sure. And one of the nice things about winning the Drake Award in 2019 was I got to meet him again. I only met him a couple of times before he died, but he was always extraordinarily generous with his time, and so I'm really lucky that I got to meet him. So as for why they gave me the award, most of my career since graduate school has been in finding exoplanets, planets around other stars. Now that's the the second and third term in the Drake equation. What fraction of stars have planets? And then what's the mean number of Earth-like planets per star? That, when Drake wrote the equation down, was totally unknown. And they had reasons for why they thought the product of those numbers was kind of like 1 per star or 2 per star. But it turns out in retrospect, those reasons were completely wrong. They didn't know. And when I started in grad school, we knew that at least a few stars had giant planets. There were about 20 known when I started grad school. And now we know that we know of thousands of planets all throughout the galaxy. And my work has largely been about finding those planets and characterizing them. And so because the field was so young when I started working on it, my work had a lot of impact because there weren't many of us in the field. So I kept track of the number of exoplanets. I wrote a lot of papers on how to pull exoplanet signals out of noisy data and how we study the stars to understand the sources of noise in the measurements that we're making. And then it was only 5 or 6 years ago that I actually got into technosignature search, that I got into SETI. But once I got into it, I started publishing a bunch of papers, and I think the SETI Institute must have really liked them and thought that they were influential.
So I guess since it's been pretty recent in terms of diving into technosignatures and the content around it, let's dig into that a little bit, if it's okay with you. The evolution as a field of research, we've talked about Fermi, we've talked about Drake. They have both posed very essential question when it comes to understanding and recognizing the potential number of extraterrestrials that might be considered somewhat intelligent, or intelligence as we define it. But there was somebody else who was doing something very interesting on the other side of the planet around the same time, Nikolai Kardashev.
Mm-hmm.
So the Russian astrophysicist who developed what we now know as Kardashev Scale. Perhaps what is the Kardashev Scale, and can you explain how relevant it is to your own research and searching for technosignatures?
Yeah, absolutely. So it was around the same time. It was just a few years after the Drake equation was written down that Soviet astronomers got interested in this. Radio astronomy was still young, and they had their own ideas about how you'd go about looking for signals. And Nikolai Kardashev was a young radio astronomer. His advisor was Yosef Shklovsky, who was a charismatic promoter of the search for life in the universe in general, very influential. And so they started, inspired by Drake and by Cocconi and Morrison, who had done the theoretical work the same year, started their own search on communicating with extraterrestrial intelligence. And one of the things that Kardashev wanted to understand was how strong a radio transmitter might I expect? How far away can I look at a star and expect I might see a signal? And so he just made this outer limit calculation. Like, what's the most energy? Like, what's the most powerful radio signal we could create if we put all of our resources towards it, all our power towards it? And so we called that a type 1 signal. And then what if we used all the energy available in the whole solar system? And that basically means all of the sun's output, because that's where all the energy is. And he called that a type 2 civilization. And then he said, all right, well, let's travel among the stars and use all of the energy in the whole galaxy. And he called that a type 3 civilization. Now, there's a lot wrapped up in this calculation. The way I like to use it is simply as a way to index or quantify how much energy is available to a species that might be, used in a way that we could detect. But certainly at the time, there was, this Soviet political philosophy that Nikolai was steeped in, and they were thinking about this in terms of human progress, humanity's future, and we continually use more and more energy every year. Our rate of consumption keeps going up, and we do that exponentially. And so, if you extrapolate into the future, it's we'll be a type 2 civilization in just a few thousand years. Now that's a silly extrapolation. You have to think about Malthus and who's doing all of this growth. And so I try to stay away from all of those social underpinnings in it, but it certainly is still out there that people imagine that humanity's future is to collect all the energy from a star. Nikolai wasn't alone in this. Also, over here, Freeman Dyson, before Nikolai published that paper, wondered what the maximum amount of technology and living space any species could have would be, and recognized that the solar output was the outer limit of how big humanity's future could be in the solar system. And so he imagined completely surrounding the star with solar panels. And he didn't imagine this as a huge engineering project that the species undertook. He just imagined that humanity would migrate to space. They'd want to live out in space, and they'd collect energy from the sun. And as long as our numbers keep increasing, as long as we keep growing, you'll just collect more and more starlight until you've used it all up. And that's the only physical limit to the growth of humanity and its technology. And so that in itself was inspired by certain notions of human progress that Freeman Dyson had in the early 60s. And that's what Nikolai was picking up on with a slightly different philosophy from a Soviet perspective. I find the framing really useful because it helps us categorize what we might be looking for. We might be looking for a galaxy that's completely endemic with technology. And so we might loosely call that a type 3, even if they haven't put a Dyson sphere around every single star. Or we might just be looking for very big technology in the galaxy, where a few percent of a star's light is being used for technology. I would still call that a type 2, even if it wasn't a complete Dyson sphere. Or, it might just be a radio transmitter on a planet somewhere, and I would call that roughly a type 1. So a lot of times this scale, this Kardashev scale, is seen as a scale of progress. And certainly you can't be a type 3 until you've already been a type 2. And so in that sense, it's cumulative. Our most sophisticated computers use less energy for every calculation than older computers. And so more sophisticated technology might be able to make do with much less. They can do the same amount of work with less. And, so in some sense, advanced technology, one way you might want to measure it is how efficient things are and how little energy it uses, not how much. I will point out, though, that even as our computers get more efficient and use less energy per calculation, they consume much more energy than they did 50 or even 10 years ago. As they become more efficient, they become more useful. And as they become more useful, we devote more resources to them. And so it's not at all clear what the advancement level of a technology, how that would map to size. Also, we should avoid imagining that there's a line of progress that all species will follow, that it's inevitable that if you have technology, that technology will grow, that there's a certain sequence of events that will happen. And so I think both Dyson and Kardashev imagined that this was a sequence that other species would necessarily follow and that was in our future. But we don't have to assume that, in our modern searches. We can recognize what the anthropologists have been telling us for a long time, which is that that's not the way it works. An analogy I really like is to evolution. The evolution of species creates creatures of different sizes. And remember, all species on Earth are equally evolved. We've all had the same amount of time to evolve. So when we say like a simple organism or something, it's not like it's less evolved. It's just as evolved. And in fact, single-celled organisms have some fantastic, ways of metabolizing and doing stuff inside its cell that we don't. The variety means that there are going to be some big things just by chance. And so we can see things like sequoia trees or blue whales or elephants or giraffes. And it's not that they're the most advanced because they're the biggest. It's not that evolution is directed towards big things and all, amoebae can hope in a billion years to be a sequoia tree. It's just that there are some big ones that just happens. And so in the whole menagerie of life, the whole menagerie of life in the galaxy or in the universe, we're looking for the sequoia trees. And doesn't mean they're advanced. It just means they're big. And if they're big enough, we'll see them.
So you may have answered this already. I just wanted to ask you how the Kardashev Scale relates to your work right now. It sounds like we're looking for sequoia trees,
Yeah,
or maybe is there something else? Is the Kardashev Scale relevant,
right.
or is there another way to frame the search for technosignatures?
Yeah. So one of the most challenging parts of SETI is knowing what to look for. Um, you know, because it requires us to guess what they're doing. And so we can say, okay, they're using a lot of energy, but how? In what way? And what does that mean in terms of what we can detect? So what Frank Drake and Kokoni Morrison and Nikolai Kardashev were thinking of was that they would put it into radio signals. And at the time, our radio detection technology wasn't very sophisticated. And so they had to hope that they could guess the right frequency and that the signal would be very strong and directed at Earth, because otherwise they had no chance of finding it. And so for a long time, there was this necessary assumption or hope behind SETI, which is that they're trying to get our attention. And that also came along with all sorts of philosophies about what the message would be like and why they are sending it and whether they're benevolent or malevolent and all of that. And so into that goes how much energy is in that transmitter. The neat thing is that you don't even, a type 1 species is enough to send a signal that we can detect here if they're trying to get our attention. The other thing we can do is say, okay, maybe they're not, they're just using energy. Could we detect that? And the answer is yes. All energy use generates waste. And that sounds weird because we have like a more efficient car or a more efficient computer. But that just means that to do a certain thing, it uses less energy. The energy it uses is still, once the energy is used up, has to be expelled. So it's waste not in the sense of energy I could have used but didn't. It's waste in the sense that you can't destroy energy. And once you've pulled all the utility out of it, all the exergy it's called, once it's at a maximum entropy state, you have to get rid of it. So you can think of your computer. Your computer is very efficient. But you draw all this energy in from the wall, and your computer does things, and it lets you watch this video. And when it's done, it just gives it off as heat, and the fan runs, and the computer heats up. So if they're using energy, no matter how efficiently they're using it, it doesn't matter. All that energy needs to be coming out either as something like radio waves, which we might detect, or just as heat. And if you use enough of it, like a type 2 civilization might, that'll be detectable. We should be able to see that heat. We see a star that has no business be having all of that extra infrared heat radiation coming off of it. So the first project I did was looking for heat from technologies elsewhere in the galaxy. So Dyson spheres are galaxies that are filled with Dyson spheres. That project came about because NASA had launched a satellite called WISE that was actually sensitive to this kind of heat. And it was the first time that it was possible for us to actually go look for these sorts of things. It turned out to be completely plagued by other things. There's so many things that give off that kind of radiation, so many to weed through that it's only recently with the launch of Gaia that we've been able to sift through it and do a better job. But one thing we were able to do is show that there aren't any type 3 Kardashev civilizations near the Milky Way galaxy. If there were a galaxy filled with Dyson spheres, we definitely would have seen it. Like 100%. It would have been so obvious. In fact, it would have been obvious a while ago. Someone would have stumbled across it. But what we were able to do is go looking more rigorously and just ask, okay, not a galaxy filled with nothing but Dyson spheres, but what about 90% or 80% or 50%? And we were able to show probably not. We found a few interesting galaxies that were consistent with that. But they also showed signs that they were probably a rare kind of galaxy called a starburst galaxy that produces a lot of this heat for other reasons. And so I would love funding to go follow those up and take a look at them and confirm that they're starburst galaxies. And I'd love to do a more sensitive survey of galaxies, because what we did was actually pretty crude. And today, with our understanding of galaxies and the light they give off, we can actually do a much more precise job. So we called that glimpsing heat from alien technologies, or GHAT. And I'm now involved with other searches looking in our galaxy for individual stars that are giving off far more infrared heat from energy use than they have a right to based on what kind of star they are. Because some stars do that anyway.
Well, let's follow up with that one. So, how do you separate out the natural bright star versus the unnatural or artificial bright star?
So the nice thing about looking for communication, like radio waves or laser signals, is that if you find it, you know it's from technology. There's just no way to create a very narrow bandwidth radio signal naturally. And so the radio telescopes, they detect these all the time. They're from us. And their big problem is just that we generate so many radio signals. It's very hard to distinguish those from the ones coming from space, even with a sensitive radio telescope. So that's where we spend almost all of our time in Radio SETI, is trying to weed out the terrestrial interference. With waste heat, it's a different problem. Like, we can be sure that we're seeing extra infrared radiation from the star. The question is, why would we think it's from technology? So when stars are very young, they're surrounded by protoplanetary disks. And those disks eventually form planets. But in the meantime, starlight hits them, they heat up, and they radiate it away. Now, they're not doing calculations with that. They're not, running factories or doing whatever it is advanced, alien species do. They're just heating up and then radiating it away. But to us, it's all the same. We can't tell what they're doing. We can just tell the light's being intercepted and re-radiated. So we don't want to look at any young stars. Fortunately, young stars tend to have lots of other properties that easily distinguish them, and we know where they are. The next problem is there are other things that look like stars that give off infrared radiation. And the big confounder here is quasars. These are not stars at all. They're distant galaxies that host supermassive black holes in their centers that give off lots of radiation, which we see as infrared radiation. But it's very hard to tell that they're galaxies in advance. They just look like little dots of light. And so there are a lot of those, and some of them happen to look like what we're looking for. And so that just completely overwhelms any search you try to do. So fortunately, the European Space Agency just launched a mission called Gaia that measured the distances to virtually everything that looks like a star in the whole sky. I mean, billions and billions of stars now have their distances measured. And that clearly allows us, along with other things, to tell what are the quasars. I forgot there are giant stars with like dust in their atmospheres. They're very cool as stars go. They're also a big problem. They look just like Dyson spheres. And so knowing how far away these things are tells us how bright they are. Knowing how bright they are says, okay, that's a young star, that's a giant star, that's a quasar. And lets us focus on things that look like they're, for all purposes, basically just like the sun. They're middle-aged stars just floating around, probably have planets, and don't have any right to have a lot of infrared radiation. And there are very few of those. There are still a few confounders. Some of these stars have debris disks. So it's like the asteroid belt or the Kuiper belt in the solar system, except way more stuff, way more of these little bodies orbiting it. And when they collide with each other, they generate dust. And it'll give off infrared radiation, and we can detect that. The good news is that those are really interesting. We like to find those, and we like to study why some old stars have these very large debris disks. And so when we go looking for Dyson spheres, we'll find a lot of those, and those are interesting. And so that's great. We get to do natural science while we're looking for alien technology.
Okay, so let's bring technosignatures back down to Earth. Looking at technosignatures as, say, measuring our own energy consumption or our own waste heat. I know in my lifetime the population has doubled. Energy use is growing exponentially. So what is our future here on Earth? I mean, what kind of waste heat could be detected by an alien, not just now, but say in 100 years or maybe 1,000 years?
So on Earth, we're becoming more attuned to the fact that our technology has a feedback on the planet. The most obvious one is global warming because of fossil fuel use. Now, if we weren't using oil and natural gas and coal for our energy, that wouldn't be such a problem. And there, hopefully we will get that under control and mitigate it. But we have other ways that we have this negative feedback with the biosphere. That CFC is destroying the ozone layer. This mass extinction going on for lots and lots of reasons, and so we have to be careful if our technology is going to continue to grow in its footprint, that footprint, not harm the biosphere that we rely on to exist in the first place. So we know we can't extrapolate much farther in the future without some kind of cataclysm. And so that's an unstable future for humanity. If humanity in the future is going to have technosignatures, if our L is going to be large enough that we might be detected by other species, it has to be done in a way consistent with our biosphere, which is not what we're doing right now. Hopefully we're moving in that direction. You mentioned population. Most population predictions don't involve more than maybe one more doubling of the human population, because as humans get more economically secure and with technology and education, birth rates do drop. And so I'm hopeful, at least, that we're not going to have the population bomb that just wipes us out. I think climate change is probably a bigger problem. But at any rate, there is this hopeful future where we asymptote to something sustainable, and then off we go. So then we just get into just thermodynamics, like how much energy can we use? After all, even if the population were to shrink, computers are really useful. Our server farms, clouds, are incredibly useful. We can do fantastic things with them. And but we're already, straining as much energy as we can produce. Like a significant fraction of all the energy humans use is to run computers. And we've already seen, like now we've got these chatbots and things that were trained using obscene amounts of energy to create them so that we could all use them. So the issue is, where do we get all of that energy? And so if we're not using fossil fuels, we want to do something renewable. That's ultimately sunlight, whether it's solar power or it's wind power or wave energy. We could also do nuclear power, which could give us a bit more, but or even maybe a lot more. But we will eventually start to hit a new problem, which is that that's more energy than the Earth's biosphere is supposed to have injected to it. Solar panels aren't so bad because that's energy that would have landed anyway. But nuclear power, that's energy that wasn't supposed to be here. And we can put solar panels in space. In principle, we could beam that energy back to Earth, but that's, again, more energy than we're supposed to have on it. So right now, it's not a big problem. The amount of warming on the Earth because of the extra energy we produce is very small, just negligible compared to other sources. But if we were to keep doubling our computing power too many more times, like 10 more times, that would be a huge problem, and it would completely alter climate on Earth. So ultimately, the solution is that you've got to use that energy somewhere else, not on your biosphere. Like go cover Mercury in solar panels and build your supercomputer there, or build your factories on Mars, where there's no, as far as we know, there's no biosphere to harm. And so maybe the moon is the best place to put our computers of the future and beam our energy to. And so it's very similar when we're looking for other technologies. They might need to have very big technologies. Those would seem to be inconsistent with a biosphere, but that's okay. I mean, maybe their home planet is over there, and then all the technosignatures that are loud enough, big enough, energy intensive enough for us to detect are on other planets and other star systems, and so on. So yeah, if we're looking at Earth's technosignatures, my hope and expectation is that the long-run future of humanity with a sustainable biosphere involves pushing a lot of that stuff off planet. But we will eventually start to hit a new problem, which is that that's more energy than the Earth's biosphere is supposed to have injected to it. Solar panels aren't so bad because that's energy that would have landed anyway. But nuclear power, that's energy that wasn't supposed to be here. And as you mentioned, Matthias, we can put solar panels in space. In principle, we could beam that energy back to Earth, but that's, again, more energy than we're supposed to have on it. So right now, it's not a big problem. The amount of warming on the Earth because of the extra energy we produce is very small, just negligible compared to other sources. But if we were to keep doubling our computing power too many more times, like 10 more times, that would be a huge problem, and it would completely alter climate on Earth. So ultimately, the solution is that you've got to use that energy somewhere else, not on your biosphere. Like go cover Mercury in solar panels and build your supercomputer there, or build your factories on Mars, where there's no, as far as we know, there's no biosphere to harm. And so maybe the moon is the best place to put our computers of the future and beam our energy to. And so it's very similar when we're looking for other technologies. They might need to have very big technologies. Those would seem to be inconsistent with a biosphere, but that's okay. I mean, maybe their home planet is over there, and then all the technosignatures that are loud enough, big enough, energy intensive enough for us to detect are on other planets, other star systems, and so on. So yeah, if we're looking at Earth's technosignatures, my hope and expectation is that the long run future of humanity with a sustainable biosphere involves pushing a lot of that stuff off planet.
And I guess a follow up would be that, is there a real value to us reducing our waste beyond just the scope of preservation of our biosphere? Can anything be done looking at that question from the opposite spectrum? Is that us saving is not just about preservation, it's also about protection.
Protection from what?
The way that I'm looking at this is that you want to be able to be safe because, as humanity, you are a type 1 civilization, and you don't have the capacity to be able to overcome anything that is beyond that similar type of civilization.
Yeah.
So for you to be able to reduce and protect you and your civilization, you could reduce your footprint overall.
Right.
Because we always look at it from a self-centered perspective, is that how do we save our biosphere? But it's also like the larger civilization perspective, which is how do we protect Earth from potentially
bad aliens?
Alien invasion, right? The bad aliens.
Yeah.
Right. So there is a concern that if we get detected, that the aliens will come here and eat us or whatever. And if we follow this idea of technological advancement is linear, and if you're advanced in one way, you're advanced in another, then if they have the spaceships to get here, surely they will have the military might to conquer us, and all sorts of analogies to human contact and colonization and things like that. And I mean, that's a very common concern, and obviously it's a common trope in the media as well, when we tell all of these narratives about human contact among civilizations. I am personally not so worried about this. There's a few reasons, or I'm not worried about it. I feel like, if they wanted to come here and take our planet, they would have done it by now. They already know the Earth is here. They already know the Earth has a biosphere. The biosphere's been detectable for hundreds of millions of years or billions of years. I'm not sure why getting radio signals from Earth would suddenly inspire this military invasion that we would have to worry about. And so I really don't worry about it very much at all. The effect humans have on the planet is very small in a cosmic sense. Like looking back on Earth and trying to tell technologies on the planet, going back to my earlier point, radio waves are just barely there, but other things like maybe you could pick up their CFCs in the atmosphere. They're actually kind of obvious, even at trace amounts. Maybe you could track land use changes, but how as an alien you would know that wasn't just some new species of tree or something. I don't know how you'd be able to tell. So no, I don't worry too much about that aspect of contact. I know that for people who worry about our intentional transmissions to aliens, like there are people who send signals into space that are meant to be detected by aliens, that gets a lot of people upset because they're worried that they'll come and look at that, they have a technology, now is the time to invade or something. And I suppose it's logically possible, but like I said, they've known the Earth has been obvious, much more obvious than the signals for so long that I don't worry about it. I don't pay much attention to those efforts, which I think have no chance of succeeding anyway.
So I'm going to move on. I read that Jill Tarter, one of the founders of the SETI Institute, is the one who came up with the word technosignature.
Yeah.
That's really cool. I didn't know that.
In 2006, yeah.
Oh, yeah? Well, maybe you can talk about that a little more. But I was going to say, I attended virtually the 2020 Order of the Octopus conference,
Uh-huh.
which I believe is housed at Penn State, where you're at.
We support it however we can, but it's an independent thing. Yeah.
Oh, okay, gotcha. Well, I assume there were a few of your PhD students there that gave some talks, which were really fascinating. And the word technosignatures is very broad. We talked already about waste heat and radio communication signals. So, what are some of the key technosignatures that are being studied right now, either by you or your PhD students or say others?
Yeah.
Technosignatures that we haven't really covered yet that are interesting or relevant that we haven't discussed yet.
Yeah, so we've talked about radio waves, which is where most of the work has been done. It's the most mature field. It's where most people are still working. And we've talked about Dyson spheres and waste heat. The one that I think is ripe for a lot of progress is also from the same era, from the early 60s. Ron Bracewell said that if your point is to convey information, light, radio waves, is a really slow way to do it. And just as an example, like if you want to watch a movie and you want to have the movie to play it, if you stream it, you don't download the whole movie at once. No matter how high bandwidth you have, it's going to take a few seconds, at least, probably many minutes, to download the whole movie. But if I just hand you, a DVD or a Blu-ray, you've got the whole thing in like less than a second. The point is that physically inscribing information in media and then sending that medium, mailing it or whatever, is a much higher bandwidth than you can achieve through radio or light communication or something like that. And so his point was, if you want to send Earthlings all of this information, the Encyclopedia Galactica, you can do way better by sending a ship. And it takes a ship a long time to get there. But by the time it gets there, you will have sent more information than the same amount of time with radio waves. And so he says the galaxy is probably filled with lots of these ships. Like it only takes one species that thinks it's cool to put these messages in a bottle and send them out. And, they can make as many as they want, send them to send many of them to every star in the galaxy. And so there's this idea that we should be looking for technology in the solar system. Now, this idea has been kind of taboo for a while because there's like all the face on Mars nonsense and pyramids on the moon, and then all this ancient alien stuff, just utter nonsense, has really poisoned the well if we want to talk about whether aliens are actually already here. And people will immediately go to UFOs and all of this other stuff. But we still want to try. We still want to try to say, do we know that there are not alien spacecraft in the solar system? If so, how big a spacecraft would we have noticed by now? And no one's answered this question yet. It's surprisingly tricky to do. So looking for probes or ships in the solar system, or even looking for things on the surfaces of planets and so on, that might have indicated that they were here in the past, is something that I think is becoming something more people are starting to become willing to do. And so solar system SETI would be one more branch that's relatively unexplored. Earth, it turns out, is a terrible place to look for alien artifacts because life destroys everything on the surface in years. And so, nothing old can be on the Earth because of life. Almost. That's an overgeneralization. But compared to Mars, it's just awful. So another thing we could do is we could look at other planets and try and see other technosignatures like Earth has. And so we know that there are planets roughly the size of Earth where there could be liquid water on the surface, or even if not, but that will have atmospheres that we will be able to probe. Like, within the next 20 or 30 years, we will have space observatories that are probing and determining the compositions of atmospheres around other planets in other star systems. This is just amazing. We'll be looking for biosignatures, among other things. We'll be looking for methane and oxygen and ozone. And but what if we see CFCs? If we see those, we're going to have to get very creative to understand how you can make CFCs naturally. It's not impossible, but there's no reason there'd be so much of it that you could see it in the atmosphere. CFCs just don't get produced in any significant numbers, and they break down so fast that you expect to never be able to see them naturally. So that would be very interesting. It wouldn't be proof positive, but it would persuade a lot of people. So that idea is actually quite recent. It did not come from the 60s. But this idea that we can do it's basically archaeology on other planets. that we can see artifacts of technology on other planets. You also earlier asked about waste heat on the Earth and how you might see that. When we image these exoplanets, if we do it at infrared wavelengths, thermal infrared wavelengths, where we look for Dyson spheres, we might be able to piece together as the planet spins what the surface map of heat is. And so that's another way we might look for heat, is that it's localized in cities or something like that on the planet. It's even possible that they might just have so much artificial lighting we could see it. So the dark sides of these planets should be basically black except for lightning, like just completely dark. And so, if we can see that there are continents with lights on them and stuff, and I don't mean we take a picture and we'd see the continents, but we should be able to tell that the night sides have light based on how the brightness of the planet changes as it spins and goes around the planet. It's conceivable we can pick that up. So those are a few more paths.
Okay, so from a practical point of view, how are we actually going to do this? I mean, are we using space telescopes, or are we beaming things off the moon eventually? Where are we right now with the technology?
Yeah.
What's feasible?
And if I can just tack one more thing on there on that question, is that all of this research that is in the effort of trying to find something cost billions and billions of dollars in order for you to actually execute this and come up with some sort of basic understanding. Yes, it's a beneficial of science, but you as a scientist, how would you actually engage to convincing the normal public individuals to try and help them see that where we are versus where we need to get to for the sake of science is useful?
Okay, so there's a bunch there. The good news is that most technosignatures that we might detect, we would detect using the kinds of instrumentation that we use for astronomy anyway. So, if I say, let's go look for CFCs on alien exoplanets, the good news is NASA's already doing it. They're not looking for CFCs, they're looking for other things. And so they might make slightly different design choices if they were completely bent on SETI versus biosignature detection or just general exoplanet characterization. But for the most part, we can piggyback. The main challenge is getting NASA to fund people to think about technosignatures as part of that mission, to make sure that they don't exclude useful technosignature searches from the designs of these missions, just like they make sure that the missions are useful for biosignature search. So the good news is that it does not need to be a huge amount of effort, like an entirely new kind of science that's being developed. All the science used to develop technosignature search can be used for the rest of astronomy as well. Now, there are exceptions. Certain hardware is very SETI specific. And so if you want to look for laser flashes, like they're doing it at UC San Diego with a project called PanoSETI, that's new hardware, but it's not billions of dollars new hardware. It's the kind of scale of hardware that you might do for just one more astronomy project. So as for convincing people why to spend money on it, well, why spend money on it at all? I think SETI actually has a way easier time of that than most sciences. There's a lot of basic research into stuff and you don't know if it's going to have any application. When you ask people to justify it, it's like, well, you never know where it's going to take you. And, we should explore blue sky research, and the National Science Foundation is wonderful at funding this sorts of stuff. It's a really special thing about the United States, how much money we put into science that doesn't have any immediately obvious application. But SETI is not like that, actually, because, if you ask the public, is this the kind of thing NASA should work on? They'll overwhelmingly say, of course we should be looking for alien life. At the very least, we need to know what's out there. There's also this just, wonderful philosophical question of whether we're alone that has a lot of resonance with so many people. It's the reason sci-fi is popular and people really want to know. And so I think actually in all of astronomy, SETI probably has the least difficult time justifying itself to the general public. Now, a more common objection is something like, why are we spending money on astronomy that doesn't help people when, we have people that are hungry, we have people that are unhoused, all this poverty in the world, all these diseases we could be curing instead. And, I'm all for that. My answer is simply that we have plenty of resources that we can allocate to all of these problems. We do not have to choose. It is not a contest. If you give me the option of feeding starving children or doing SETI, I feed the children every time. I just reject the idea that we have to make that hard choice. We spend trillions, globally, probably hundreds of trillions of dollars on so much stuff that doesn't help people. And a tiny fraction of that money could be spent and completely eradicate world hunger, could give everybody a house. And we'd still be able to take a tiny fraction of that and spend it on astronomy and do way more astronomy than we're doing today. And so I just see it as a false choice.
So I just have one more question here. Okay, so over the next 5 years or so, the amount of missions to the moon is going to increase, and there is a positive likelihood that far side of the moon is a very, very, very fantastic place for radio astronomy and for a lot of the things that are housed under the technosignature umbrella.
Yeah.
Is there a possibility that more and more scientists like yourselves will try to actualize a lot of these, exploration benefits that are coming down the pipeline to further understand from different mediums, right? Because the moon is an entirely different medium.
Yeah.
So curious about that.
No, I mean, all this new space stuff, whatever you think about it and the people that are behind it and all of the social implications, the impact it's going to have, that it could have on science, is incredible. NASA right now, will spend $1 to $10 billion on a space observatory. And a lot of that money is tied to the fact that getting off the planet is expensive. So you only get one shot. Like, you're only going to launch one of these things. You're not going to launch 100. And so it has to work. And getting all of those nines of reliability on every single component is very expensive. And the rockets are expensive. If it's possible, you also don't have a lot of space. So these things have to be super light. They have to be super compact. And that makes everything expensive. If it's possible to just launch a telescope into space and doesn't cost that much, then you could launch 10. And if 5 of them fail, whatever, you got 5. That's great. And so that completely changes the whole risk profile and budgeting of these missions. And it means we'll be able to do more experimental stuff. We'll be able to prove stuff works in space much more cheaply and easily. The development cycle will get shorter. If things like Starship go even half as well as advertised, which I don't think is likely, but I'm hopeful. I'm hopeful. If that really happens, that's a complete game changer for astronomy. We'll be doing amazing stuff. You mentioned the far side of the moon. The reason we like the far side of the moon is that there's virtually no radio frequency interference from Earth. And so I said the hardest part about looking for radio signals from space is that we get millions of signals from Earth. And from the far side of the moon, that all goes away. And it just becomes much simpler. So that is a big expense, trying to build something on the far side of the moon. But it would be a much more powerful and much more efficient search if you could do it. And if we don't contaminate the far side of the moon with radio signals. And so it would have to sort of remain a nature preserve, most of the back of the moon, even from orbiters. They would have to go quiet when they're over there or stay within a certain range or something. It's going to take international cooperation to happen, but it would be pretty amazing.
Well, I'm curious about that now because you're lobbying for that as an astronomer.
Yeah.
Like, let's make this dark side of the moon, this backside, a safe haven for science, yeah?
Yeah. The International Academy of Astronautics, which for historical reasons is where the international SETI efforts are, have a home, a lobbying home. They've been working on this project for a while and trying to, sort of get countries to agree that that's a good idea. Because, if you prescribe it ahead of time, you just say, hands off the far side of the moon, then, in their ambitions for the moon, they can work around that more easily. If you try to do it after they're already there, it'll never work. Just like Starlink is just a disaster for ground-based astronomy, just a disaster. And, astronomers didn't see it coming. Like, we didn't realize that if we took big images of the sky, they'd all be contaminated by Starlink satellites every single time. But if we had known that ahead of time, then before anyone was even thinking of Starlink, we could have gotten some kind of protections involved. And then when Starlink was designed, it would have been designed in a way that didn't hurt astronomy. But to get them to change now, it seems impossible. So I'm hopeful, that we can do that. And so certainly I will lend my support to that. I lend my support to, lots of efforts like that to make sure that we can continue doing science, and that we don't, as we develop new technologies, that we do it in a thoughtful way that preserves the work we're trying to do.
So I know we are wrapping things up, but I wanted to ask one more thing. I was actually shocked. You said earlier that the public was very much interested in looking for technosignatures or interested in SETI, and I say shocked because mostly I have been under the impression that SETI has a history of being frowned upon as if it's not a real science. And I know you're the director of Penn State's Extraterrestrial Intelligence Center. When I hear that word, I think of the movie Men in Black.
Oh, okay.
But but the center is an academic think tank
Yeah, exactly.
advocating for SETI and formalizing the science behind SETI's methodologies and really training the next cadre of SETI scientists, which is fantastic.
Yeah.
So I guess my question was, do you think the field of SETI is still combating that little green man bias?
Yeah, there's a lot of different angles where it's challenging. There's definitely a sense among scientists that maybe it isn't a real science or that it's based on a lot of outdated assumptions. Um, there's, I mean, there are some people that think looking for biosignatures is silly and that's not a good thing that we should be working on. But for the most part, I have found general acceptance. I mean, especially when we frame it the way you said, in terms of making it a discipline and putting it on rigorous theoretical grounds and stuff, I generally get very positive receptions. At least to the point where the people that think it's silly keep their mouths shut, which I think is, good enough. I'll take it. But we do need more training. When the government shut off the spigot in the 80s and 90s, that moved all of this work to research foundations and out of academia. And with a few exceptions, like at Ohio State and Harvard, people weren't being trained in it. I mean, there's no curriculum, there's no textbook, there's no standard definition of terms, there's none of the stuff that academics do at universities when developing a discipline. So that's what we're trying to do. We're trying to give it that academic foundation. And I think that will help even more. The other thing is that, NASA's resistance to working on it came from just a couple senators. This wasn't like this broad thing. I mean, it was Congress liked it. They thought it was cool. Now the push is actually the other way. There's a lot of congressmen and senators that think this is really important and are poking NASA. Why don't you do this? And so that has caused NASA to push back and say, oh, look, we do. Here's a few things we funded here and there. I've noticed that people are more receptive to it. And some of it is cultural. Frankly, when Congress did this, the SETI Institute, Carl Sagan and Jill Tarter, they made a big push to try and get public support as a way to try and get philanthropic money. And it worked. They did get a lot of philanthropic money for it. But one of the things they did was they tried to get Hollywood's attention. So Carl Sagan wrote the novel Contact, and then it was made into this big movie Contact, which a lot of astronomers have seen. And the framing of that movie is how unjust it is that the government won't fund the field. And so now I think we have a whole generation of astronomers, sort of my age, who are influential and are doing this kind of work that have that attitude instead of another attitude. And so I think that's great. Carl Sagan deserves a lot of credit for insisting that looking for life in the universe was not just, scientifically credible, but scientifically important and something that should be, on the top of the lists of things that we should be doing.
So I guess part of that is that in the next 10 years or so, as this field evolves and continues to evolve, do you imagine that there's going to be a shift almost organically from foundations supporting you to more government-oriented programs coming online? I mean, just like if we think about the correlation between new space and old space, I think that change in dynamic has also created some very interesting propositions, right?
Yeah.
Could this also become more than just science per se, I imagine?
In terms of the shift, I don't know. I'm not sure how to think about it. You talk about old space and new space. I'm not sure America collectively is spending more money on space than it was, maybe a little. But for the most part, it's moved. Like NASA used to do almost everything involving rockets in-house or with a few defense contractors, aerospace contractors. And now there are new players in town that are innovating and using that money in new directions that are very exciting and different. I'm not sure what the analogous shift would be for funding SETI. because the government doesn't fund it, anyway. So my hope, my plan is that we can put SETI back where it belongs under the astrobiology umbrella. Because it used to be if you went to an exobiology conference, there'd be SETI and there'd be talk about other kinds of life in the universe. When NASA moved in a big way to trying to find other life in the solar system and elsewhere in the universe, it said, we're going to call it astrobiology, and they put a lot of money into developing it as a discipline and with partnerships with universities. But it was strictly biosignatures and life on Earth. It was not technosignatures. And so my plan is to point out that is an artificial division and get SETI under the astrobiology umbrella, because that NASA understands how to fund that, and Congress understands how to fund that. And then we can just, play with everyone else and compete for government money the same way everybody else does. But it'll take time. We're a young, immature field. It's hard to compete with a field that's been around for decades if it's an open grant. And so, anyway, I'm hopeful that NASA will see the value in promoting it.
So here's a question. I think one of the things is that a lot of the benefits are very economic focused when it comes to this orientation around space. Is there a possible way that if you were to do a pitch about what this field could potentially do for things on Earth?
Yeah, I mean, NASA often justifies its budget with the sort of spin-off technologies,
Yeah.
right? That we spend all this money on going to space, but the money's spent on Earth, and look at all these cool technologies that come out of it. And so we can always make that argument for basic science. I actually think that SETI almost uniquely doesn't need to make that argument. I mean, we can make it as strongly as anybody, doing astronomy or something. But I like to say that if you're a scientist and you're on the plane and your seatmate asks what you study as a scientist, most scientists have to stretch, right? They say, well, it's very complicated, but it has to do with proteins on cells which one day might help us cure cancer. And even if they do nothing involving cancer, it's plausible. But we never have that problem in SETI. Like we say, I look for life in outer space, and people know what we're talking about, and they might have misconceptions about it. And so it's nice. It's really nice to be working in a field that the public appreciates. Not universally, of course, but just much more than a lot of other fields.
So this is something that we ask everybody, is that in this case and understanding, how would you per se push this envelope and move the field of technosignatures forward to from where it's at right now?
Yeah.
Like, what are concrete steps that can be done in the next coming decade per se?
Yeah. Like I said, because it's an immature field, we need to catch up. And so that's a lot of what the Peace SETI Center's purpose is to train people, to develop a curriculum. We have courses that we teach in it at the graduate and undergraduate levels. We're going to have a textbook on the topic, and give it the academic rigor that will let it, show its value when we go to NASA and ask for money to do stuff. So that when they say, what would you spend the money on? We have very specific plans that we've justified rigorously that they will appreciate. I think we need to educate the public so they understand where the challenges are and what it is we're doing. Understand why we're not looking for UFOs, why we dismiss claims of, the face on Mars and things like that, that it's not snobbery, that, there really is a difference in what we're doing. It's about a culture change at NASA and maybe at the NSF too, about whether this is worthwhile and whether they'll get in trouble with Congress if they support it. And about letting us compete for funds within NASA and even creating special funds that we can use to develop the field better.
So, Jason, it's been great having you, really fun. But our very last question, what I'm pretty sure all of us want to know, will we detect any technosignatures within our lifetime?
Well, the cheap and silly answer is, of course, because we produce them all the time. And so that's really annoying, actually, because we want to find the other ones. But if you mean finding ones built by something other than humans out there in space, I really don't know. I know a lot of people in the field of SETI are in it because they expect there's something to find in their lifetimes. And I know that Frank Drake and others expressed that optimism, that a detection would be made. And I really, it's possible we're alone in the galaxy. That's a possibility, and I don't know. But I do know what Cocconi and Morrison said in their original paper that got this all started, which is that if we don't look, we definitely won't find anything. And it's an important enough question that it's worth looking hard and looking right. And so I'm excited to be in the field when it's so young, and there's still so much looking to do that no one's done before. There's just, there might be really bright laser flashes in the sky all the time, and we just haven't noticed. There might be powerful radio beacons for us to detect, and we haven't noticed. There might be Dyson spheres in the Milky Way, and we just haven't noticed. And it's not that hard to look for them. And so doing all of these first searches is very exciting, and being among the first researchers that can say, we know these don't exist, and so on. And I think that's where the most likely way to find something is when you just look at a huge region of parameter space that's been unexplored. And so I don't know the odds, but they're much better today than they were even 5 years ago because of all the new searching going on. And that's exciting.
Yeah, very exciting. And I remember Jill Tarter, I think, likened it to a glass of water.
Right.
That if the universe was our ocean, say, we've only searched an area equivalent to a glass of water.
Right.
And also I've heard that the updated analogy is now the size of a hot tub. Is that true?
Well, right. People would ask Jill, you've been looking for decades for these radio signals. Isn't it time to give up? And her point was, we haven't been looking. We don't have all this money to conduct these searches. They did get a lot of money from Paul Allen and Barney Oliver, but that money wasn't enough to finish the big array that they were going to use to conduct the big survey. And so it never happened. And so she would emphasize, right, there are so many places to point the telescope, so many frequencies to check, so many, different bandwidths we can optimize for, that, to say we haven't found anything, therefore nothing is out there, is like dipping a glass of water into the ocean. It's not seeing any obvious fish in it and saying, the oceans are sterile. This is pointless. We should never go fishing. Her point was, we've barely begun to start to search. And yes, we did her calculation more rigorously here at the SETI Center, kind of defined its terms and made a better estimate of where we are today. And her estimate was excellent, even though she just did it sort of back of an envelope. But now we're up to about a hot tub's worth of water. And so, yeah, it's improving, but we have a lot of looking to do.
Great. Awesome. Well, let's hope we can move on to, say, a swimming pool size or ponds, lakes.
Yeah.
A couple of lakes.
I love it.
If you're still listening, a word from your sponsors, which
is essentially us. Our team works really hard
to bring you these enlightening conversations about
the future of space exploration.
And yes, you are vital for fueling our podcast and making sure that we don't disintegrate into the vacuum of outer space.
So if you like Space Forward, give us a thumbs up. And if you love Space Forward,
well, then share that love and recommend this podcast to a friend. And tune in to episode 17 and find out who owns what on the moon.